and beginning in 5, 4, 3, 2. Thank you for joining today's webinar entitled Smart Power Flow Controllers for Smart Grid Applications, presented by Kalyan Sen, Chief Technology Officer with Sen Engineering Solutions, Inc. My name is Cole, and I will be your event specialist today. All lines are currently on mute to prevent any background noise, and please note that today's conference is being recorded. We will have a question and answer session at the end of today's presentation, moderated by Phyllis Caputo. To submit a text question, look at the question and answer panel at the bottom right-hand side of your screen. Type your question, select all panelists, and click Send to get your question in the queue. Finally, if you experience any technical difficulties during today's event, you may submit a chat to the host. At this time, I would like to turn the program over to our presenters. Mr. Sen, the floor is yours.
Thank you for the introduction. Ladies and gentlemen, good morning, good afternoon, good evening, depending on where you are in the world. The title of my talk is Smart Power Flow Controller for Smart Grid Applications. So what is a Smart Power Flow Controller? An electric power grid is a network of transmission and distribution lines that carries electricity from power plants to consumers. Soon after, Nikola Tesla and George Westinghouse demonstrated the feasibility of long-distance transmission of electricity in 1890. Electrical engineers realized the need for a power flow controller for the most optimized use of the power grid. Ever since, we have been searching for that perfect power flow controller to make our power grid operate efficiently. Today, I'll present to you a power flow controller, what we call a smart power flow controller, that can operate the electric power grid in the most desirable way. The content of this presentation is solely mine. It expresses my opinions that I formed during my 3 decades-long career. First, I'll present the basic power flow controller concepts, which will be followed by most commonly used power flow controllers, future trends, and some recommendations. So what qualifies me to talk about this subject? Here is a short biography of mine. I attended 4 colleges for 14 years to receive my 4 degrees, 3 of which are in electrical engineering, and an MBA. Besides being a professionally IEEE member, I also volunteer significantly. If anyone is looking to gain a hands-on experience in your leadership skills, I suggest you take a role in running your local IEEE chapter. My wife and I tried for 6 times, and all 6 times we were the best section and chapter awards winners. It is a great experience that stays with you forever. After receiving my PhD degrees 30 years ago, I was recruited to be an assistant professor. 3 years later, I joined Power Electronics Department at Westinghouse Science and Technology Center, where my manager, Dr. Laszlo Gyugy, was forming a team to start with the development of a new set of power flow controllers. By that time, the power flow control technique is getting to be started on the new dimension. The thyristor control technology was fully developed. Naturally, the new power flow control techniques have to be based on inverter-based controllers, because that was the new thing at that time. It used to be called also voltage source converter or VSC-based. The next decade, we demonstrated the very first things in the world in this area, such as voltage regulator, which is STATCOM, impedance regulator, which is UPFC, and reactance regulator, that is SSSC. Throughout this project, I was constantly thinking, because of my business background, whether these projects would ever be commercially successful. In our department, I was the only one with a university background. We had 2 other PhDs. My role was to develop mathematical models of the FACS controllers, the control algorithm development, design the control and protection unit, TNA, testing, and full-scale commissioning. We all wrote original papers and the patents. My boss, Dr. Gyugy, took it to another level. He wrote an advanced level book. Many people wanted to know the basics first. So my co-author, who is my wife and an electrical engineer, and I wrote a book. I've given presentations like this in more details over 100 times around the world as an IEEE PS distinguished lecturer. After Westinghouse closed down, I started developing smart power flow controller at Sen Engineering Solutions that I co-founded. Our goal is to develop a smart power flow controller from utilizing the best features of all the power flow control techniques that are developed until now. Now back to the question, why do we need a power flow controller? Sometimes we need to increase the power flow through the desired transmission paths consisting of high voltage, low loss lines. Sometimes we need to decrease the power flow of a line to either redirect the desired transmission paths or to avoid a cascaded blackout if the line is tripped. We all know that electric current flows through the path of least impedance. This free flow of electricity from the sources to the loads makes the grid operate inefficiently because of low power factor, non-optimizing loading, and so on. The power flow controller controls the flow of power in a transmission line, resulting in an efficient operation of the grid. While maintaining the voltage stability, if the reactive power flow is reduced, the loss in the power grid can be reduced, resulting in less global warming. If we represent the power grid in a simple manner with a voltage source at the source end and a voltage source, maybe the back EMF of a motor at the load end, and the line just an inductive reactance to represent a basic simple power system, the power flow equations show that both active power P and reactive power Q at both ends of the lines are sine and cosine functions. The power flow controlling parameters are voltage, the phase angle of the voltage, and the line reactance. Changing one of these parameters changes both P and Q flows simultaneously, which has been the traditional technique of power flow control since the beginning of electrical engineering. Therefore, the transmission lines are never optimized to carry the highest possible amount of P that generates the most revenue with minimal Q. The transmit of P and Q flow independently, we need to control two parameters. The phasor diagram shows that both the source and the load supply Q that is absorbed in the inductance of the line when P is transmitted from source to the load. Various solutions are presented here. In the non-power electronics version of the solution, there are voltage regulating transformers, there are phase angle regulators, reactors, capacitors, synchronous condensers, and transformers. The power electronics thyristor-based technology, which is a thyristor switch is used in static Hall compensator and thyristor control series capacitor TCSC. However, the inverter uses the control switch that can be turned on and off when desired, and it's used in SATCOM for voltage control, SSSC for the line reactance control, and unified power flow controller that is a impedance control. If we examine the features of all these controllers and its advantage and benefit, we find that a set of controller offers voltage regulation that meets the operating voltage requirement of the load. A PAR offers the phase angle regulation. Another set of controllers offer reactance regulation, and ST and UPSC offer impedance regulation. These features have an advantage of controlling the power flow in the line and ultimately a higher asset utilization for the utility. The cost and complexity of these solutions vary widely. I think that the solution that is reliable, efficient, cost-effective, component non-obsolescent, environmentally friendly, portable, and interoperable must be developed for utility applications. Consider a typical scenario where the transmission line is operating with 30% power angle and has 0.5 per unit reactance. If we assume this line is carrying 1 per unit load, which is 1,000 megawatt, maintaining the voltage at both ends of the line, this line also carries some reactive power. The reactive power comes from the load end and the source end. Since we have seen the power flow equations as sine and cosine functions, we can combine them to create this circle equation. So one characteristic represents the circle or PQ relationship at the load end of the line, and one is representing the PQ relationship at the source end of the line. And it shows that for 1,000 megawatt of real power flow, we need 268 megawatt of reactive power from both ends of the line. Now, to compare various power flow control methods on the same terms, let's define three matrix parameters. Those are called reactive power index, the loss index, and the rating. The reactive power index, which is defined by the ratio of total required reactive power per unit real power transmitted. Loss index is the ratio of the current square with respect to the current square of the base current, and the rating of the equipment. All three parameters cost money. Therefore, lower the values, better it is. More information you can find at this reference. Now, I chose three arbitrary operating cases. They are 40%, 70%, and 100%. The P-flow enhancement of a power increases the reactive power flow in the line. It shows that load is burdened with the responsibility of supplying higher amount of Q as the P demand increases. The transmission line owner does not prefer to operate the power phase angle regulator at a higher P value due to the penalty of higher Q flow in terms of higher losses in the line, which, by the way, contributes to additional global warming. Using the transformer and LTCs based hardware, a series-connected compensating voltage can reduce the power angle. The same voltage with a reverse polarity can also increase the power angle. As a result, both P and Q flows increase or decrease, as we saw in the last slide. The voltage and power flow profile of the voltage regulator and phase angle regulator are well established for more than a century. So why do we need a phase angle regulator, or why do we need an impedance regulator? For a desired PQ flow, for example, this point in this figure, the line voltage must be changed from an original voltage to a original voltage with magnitude and phase angle to a new voltage point with magnitude and phase angle that may not be fulfilled either by using voltage regulator or a phase angle regulator. Impedance regulator is the one that provides the regulation of two parameters, resistance and reactance, that results in an independent control of P and Q flows, which is shown in the next slide. Besides, the impedance regulator regulates two parameters with less hardware than the voltage regulator and phase angle regulator combined. The key to impedance regulation is to create a series-connected voltage, as is shown here, at any angle with the line current. Here is that voltage which modifies the original voltage to a new voltage, and the difference is the compensating voltage. The in-phase component of this compensating voltage with respect to the line current emulates positive R. The out-of-phase component of this voltage emulates negative R. The quadrature component leading the line current emulates an inductor, and the quadrature component lagging the line current emulates a capacitor. But actual series voltage is a composite voltage that is at any phase angle with the line current. The modified voltage is confined with this circle. In comparison, the modified voltage of the line, if we use the phase angle regulator, is along this blue line. Now, this difference of the two characteristics is significant. In a power, as the flow of power increases, the demand for Q also increases at both ends of the line. The cost of increasing Q demand may outweigh the benefit of increased P flow through the line. As a result, the power flow up to line's thermal limit may not be attainable. This is a real problem that needed to be solved. An impedance regulator solves this problem. For the same three operating cases of P flow enhancement, it shows that the load is burdened with the responsibility of supplying a higher than necessary amount of Q flow when a power is used compared to when an impedance regulator is used. The loss in the line is also increasing, and the rating of the line is also increasing. Rating of the solution is also increasing. For example, in this table, it shows that for a 100% increase in delta P, 100% increase the power flow in the line, the real reactive power index is 2 versus 1 in an impedance regulator. The loss index is 7.4 versus 3.7 in a reactance in an impedance regulator, and the rating is 2.8 in a phase angle regulator versus 1 in the impedance regulator. And lower the number means lower the cost. In addition, the impedance regulator can be operated at no additional Q demand from the load. Whereas in phase angle regulator, you see the Q demand from the load side increases as well as the source side when the demand for active power increases. Now, the impedance regulation, which also maximizes the revenue generating P flow while providing the lower RPI, lower loss index, lower rating than when a phase angle regulator is used for any amount of power flow enhancement. The additional benefits of impedance regulations are independent PQ flow that increases the capacity of the line, reduces the losses in the line, transformer, and generator, and make the whole grid more efficient and less global warming. The side effect of impedance regulation with an inverter is that a series-connected compensating voltage needs to exchange bidirectional real power with the line. And one way to accommodate this requirement is through a shunt-connected solution where it shows here in this picture. The bidirectional active power goes back and forth through the DC link capacitor. In addition, both AC sides can emulate and reactance. Note that this UPFC that uses over 800 switches and thousands of components that become obsolete soon after this kind of hardware is built. Besides, this unit is not practical for relocation. Even though it is a power electronics-based solution, as you can see in the switch here, there is a transformer that has a rating way over than the rating of the power electronics. And later I will show you a solution that uses less transformer than this and no inverter whatsoever to do the same power flow control capability. Now it's worth noting at this point why a series-connected inverter is not the most favorite choice in a utility application. Each series-connected inverter needs to have a coupling transformer, and the leakage reactance of the coupling transformer reduces the most useful rating, capacitive rating of the inverter. Although in theory, the inverter can emulate an inductor, and the inverter is never designed to emulate a large enough inductor to limit a fault current. So therefore, during a fault, the inverter is always bypassed, which requires a bypass switch. And the desirable bypass switch is an electronic bypass switch on high voltage side of the line. But no one uses a bypass switch on that side of the line because it's too expensive. So cheaper solution is to use a mechanical bypass switch. But that mandates to use an electronic bypass switch on the low voltage side of the line. And this also requires an additional inductor so that inverter does not get shorted and then carry high short circuit current during the time when the electronic switch operates. So that additional inductor even reduces further the good capacitive rating of the inverter. Now, out of the 3 UPFCs that were built during the Westinghouse time, 2 were never used after the initial runs, and 1 was dismantled within a few years after installation. Therefore, its capability of reliable operation has not been demonstrated. Now, here is the result from the 1998 demonstration of the project. We just used the series-connected inverter in the top figure to emulate a reactance. Both P and Q flows either increase or decrease. So the line is never optimized to carry the highest amount of P and the lowest amount of Q. So, however, an impedance regulation is the better solution. This impedance regulation does not need to be a physical impedance regulation. The virtual impedance is sufficient. Note that the needed speed of response in a utility application is in seconds. Although a power electronics inverter is perfectly capable, and I will show you in a minute, of responding in milliseconds. So the next obvious question is, why do we use inverters for power flow control applications? So let's examine further. Most power flow controllers consist of 2 basic components, a computer control or PLC, and that implements the power flow control algorithm, and a high-power circuit capable of injecting the corrective voltage vector determined by the power flow control or optimization algorithm. Over the years, a paradigm involved that an independent PQ power flow control requires power electronics inverter technology. But is that really true? Let's examine further. We have been connecting series voltage into the line for over a century in an auto transformer and in a phase angle regulator. It is documented in this Westinghouse T&D reference book from 1942. As I presented, a series voltage can also be used to emulate a reactance or an impedance in series with the line. Now let's examine how we can build what we really need, taking into account all the best solutions from the past. Looking at the components in both phase angle regulator and unified power flow control, which is an impedance regulator, we see that both require a computer for the control algorithm implementation, instrumentation transformers and sense voltage and current, transformer, core, windings, oil, tank. The power also requires LTCs, but no inverters, and UPFC requires 2 inverters, but no LTCs. The UPFC offers the desired PQ flow control that makes the grid operate efficiently, and a power cannot offer that. It also offers the super fast response time from the inverters. Now, this is not needed in most utility applications, as we just saw. The power provides adequate response time using its LTCs. In addition, the power offers time-tested, reliable power hardware with 40-plus years of lifespan, easy maintenance, low installation, operating cost, high efficiency, component non-obsolescence, high power density for small footprint, easy relocation to adapt to changing needs with the new generation and loads, and interoperability. This leads to my preferred solution as follows. Each metric, reliability, features, line loss, global warming is checked as high or low. Along with the cost of a solution as high or low. While keeping the high reliability of the power's components, let's build a power flow controller that offers most features, lower line loss, lower global warming as a UPFC offers. That is what a low-cost solution and transformer is. No one complains about the speed of operation of a phase angle regulator dictated by the speed of mechanical LTCs. So let's not change something that is not broken. It is proven to be effective and reliable in utility applications. By the way, the idea of replace for obtaining higher response time, but there is not a business case for using this high-cost idea. If needed, the Sen transformer can also use electronic LTCs as well. Sen transformer is a combination of time-tested hardware consisting of transformer and LTCs operated with impedance regulation control technique. AST uses low-cost power circuit to provide the needed speed of response in a utility applications. Its high power density and portability is perfect for today's changing needs of the power grid. The side effect of impedance regulation, as I mentioned earlier, but in case of ST, is naturally built into the power circuit. The exchange of PQ flows both ways between the shunt unit and series unit is already there. Unlike in a UPFC, we need another inverter. If we have a specific need for a voltage regulator, just as an auto transformer, ST can do that. If we need an impedance regulator, as UPFC, ST can do that too. Please note that an inverter-based power flow controller cannot operate, and I stress, cannot operate in all of its available power flow control range. The ST is the only power flow controller that can be designed to keep the power flow control area what is needed, eliminating the waste and resulting in a low-cost power flow controller. In a line can be reduced by making the line impedance higher than its natural value, or increased by making the line impedance lower than its natural value, while line zero. Since most utility applications need a response times in seconds, LTCs in a send transformer can provide the needed. I've been mentioning a lot about power electronics. So what is power electronics? It is an electronic circuit that uses semiconductor switches to convert electrical power from one voltage, current, and frequency level to another. The speed of response in milliseconds, as I will show you soon. If you need it, it is the greatest feature. When considering a solution for a synchronous network, which is most of the time, we're already not utilizing one of the key features of power electronics solution, that is the capability of different input and output frequencies. Now let's examine the speed of response feature in voltage regulation application. The principle of operation of a voltage regulator is explained in this voltage divider circuit, when the entire power system is represented by a voltage source and a Thevenin impedance. Considering the line is reactance, it can be easily shown that the shunt-connected capacitor is the only one that increases the voltage at the point of common coupling, and the shunt-connected inductor is the one that decreases the voltage at the point of common coupling. A shunt-connected capacitor may result in an unacceptable level of voltage and current transients, which can be mitigated, as it's shown in this picture. Voltage and current transients from a shunt-connected capacitor can be in an acceptable level if a series inductor is used with the capacitor. This inductor may be bypassed after the initial transients are over. By static Hall compensator is to create a variable inductor by varying the duty cycle of these back-to-back thyristors. Banks of parallel connected capacitors and variable inductors together act as an inductor or a capacitor as a whole. This variable inductor and capacitor regulates the line voltage, as I explained in the last slide. The point of compensation of the transmission line is regulated by varying ultimately the duty cycle of these switches. This is the power electronics solution. Power electronics thyristors switch make it possible to improve the voltage profile as it's shown here, and that is good enough for most applications. Even though power electronics inverter can have a superior solution. Now it is an old idea. This is used in synchronous condenser for over 100 years. The synchronous condenser can operate as a virtual capacitor or a virtual inductor. Now why is virtual? Because the actual compensation is the voltage. This voltage as the back EMF of the motor. By varying the field current, this back EMF can be made to be lower or higher than the line voltage. For a lower voltage, the lagging current emulates an inductive effect, and for a higher voltage, the leading current emulates a capacitive effect. So this inductor and capacitor effect actually makes the bus voltage, the voltage at the point of common coupling, regulated. And since there is no significant amount of active power flow, the voltage at inside the machine and the terminal, they are in phase because there is no really significant amount of power flow into the machine. Now the response of this machine-based operation can be over hundreds of milliseconds, which may be adequate in most applications. Now this concept was taken to the next level by replacing this back EMF by an inverter, and that inverter was 1 MVA rated. It was demonstrated in ISARCO in 1980s, and this reference gives you more about that project. Here is a result from the first commercial STATCOM applications commissioned at TVS Sullivan Gas Substation in 1995. Since the inverter has no inertia, the response time for a 100 megahertz step change can be in milliseconds, in 2 milliseconds, going capacitive to inductive or inductive to capacitive with apparent no transients. Since this demonstration in 1995, only a few utilities have used this approach for voltage regulation. We see that it is a great solution for some applications, but it does not make a business case for others. Therefore, it is important to define the functional requirements. What do you need for an application? Sometimes it may be justified if the benefits outweigh the cost. And here is one such application. When an arc furnace needs compensation, we tried out using a STATCOM, inverter-based STATCOM, because the furnace has this kind of voltage and current requirement from the utility. Since the current varies drastically or randomly, the voltage drop across the source impedance, the Thevenin impedance, also drop abruptly. So the voltage at the entrance to the plant has flickers, what we call flicker, that is a random change of voltage. Now, the STATCOM provides the needed reactive power by the furnace, as you see it in this figure. In addition, the STATCOM can do more. It can be operated to exchange net zero active power, as shown by the red line, to smooth out the power demand from the utility. Now, the result is remarkable. As you see, the STATCOM not only reduces the flicker to the acceptable level, as shown in this red line, it also reduces the wear and tear of the electrodes, resulting in greater savings. So what did we learn in 2 decades after this demonstration? Well, the lessons learned is that an inverter-based solution is too good, but not cost-effective for most applications. So the STATCOM was dismantled long before its forecasted lifetime, and proven power electronics thyristor-based concept, which is tariff Hall compensator, was reinstated. We predicted this in our 2003 IEEE transaction paper. At the present time, 2 major drawbacks of all inverter-based FACS controllers are their high installation and operating costs, which is still true in today, 2017, and it will be true in the foreseeable future. Our experience shows that the inverter is an evolving technology. We have not found our dream switch yet. The dream switch would be large power rating switch, and it should require minimum gate drive circuit, minimum snubber circuit, and operate with the minimum conduction switching losses. In the last 2 decades, we have tried out various power electronic switches. The projects that I just explained, they use GTO, only less than 2 decades ago. But then came along IGCT, then came along IGBT. Today, we are talking about using silicon carbide, gallium nitride in the future. We have experimented the inverter topologies. These inverters were built with 2-level poles. Then came along 3-level poles, H-bridges, half bridges. We have also used modulators. These inverters used harmonic neutralization technique, then pulse width modulation technique, then space vector. We are still looking for the best switch topology modulator combination. Today's state-of-the-art inverter solution becomes obsolete in a few years, and its replacement is necessary. Why? Let's talk about Westinghouse-made inverters. We built inverters with GTO thyristors. Now, when a switch fails, why not use the latest switch to replace the failed switch? Well, that's not possible because the gate drive, snubber circuit, cooling requirements change from one switch to another. Therefore, it is necessary to replace the old inverter. And manufacturers would love to replace the inverters in a few years. But it won't be a good solution, a good return on the investment. So, SVG solution for a voltage regulation may not be perfect, but it's good enough. That brings up a good question. What is a cost-effective solution? And my answer is that a cost-effective solution provides most features at the least total cost, which consists of 2 parts. The cost number 1 is the solution cost, and cost number 2 is the other cost that includes loss, maintenance, penalty for generating flicker, etc. In case A, if we do not do anything to reduce our flicker, the solution cost is 0, but the penalty cost is the highest. In cases 2 and 3, the solution cost may be higher and higher as the feature increases of the solutions, and the cost 2 comes down because of the higher solution features. There comes a point when the total cost is the lowest, and that's when the solution is considered to be the most effective, most cost-effective solution. Now here is a picture that shows there are many ways to solve the same problem. Which one would you choose? If I choose to walk from A to B, my solution cost would be 0. However, the opportunity cost may be the highest. Instead of walking for hours, I could use my time to be more productive. For most people, the solution cost of one may be good enough, which brings up the topic of smart grid, which is to be more efficient. The smart grid describes a next generation electrical power system that is typified by the increased use of communication and information technology in the generation, delivery, and consumption of electrical energy worldwide. This last word, the worldwide, was added recently. Just to keep in mind that in this day and age, the world still has 20% of its population without electricity. Another 20% of the population is without a reliable supply of electricity. These numbers are even higher if we leave the advanced countries out of the calculation. And I was one of them to study all through my high school years using a kerosene lamp. So we create new definitions. They come and go. They do not mean anything to billions of people. I believe that just increased use of communication and information technology is not going to make the grid look smart for the whole world. Many places need to have a basic grid first before making it a smart grid. The grid must include more generation and its smart delivery to be relevant to the world. Currently, the least discussed area in smart grid is power flow control, which is why we are developing smart power flow controller. Now, what is a smart power flow controller? A smart power flow controller enhances the controllability in an electric power system by using the functional requirements and cost-effective solutions. A smart power flow controller is derived from utilizing the best features of all the technical concepts that are developed in the power flow control area until now. It doesn't discriminate any solution based on whether it uses power electronics or not, or whether it is stationary or rotating. As long as it performs, it's acceptable in any form. More information can be found in this reference. So the term smart in the smart power flow controller has been in existence for many, many decades. It stands for specific, measurable, attainable, relevant, and timely. If we are designing a power flow controller to meet the utility's needs, it must have a measurable matrix such as high reliability, high efficiency, cost effectiveness, component non-obsolescence, and portability. It must have realistic goals. It must be relevant to meet the timely needs. Here is an example of a smart power flow controller. That has to meet the functional requirements. If the voltage regulation is needed in addition to independent power flow control, particularly when the short circuit impedance at the point of compensation is high, a separate shunt-connected compensator may be used along with the transformer. This topology does not use any inverter to provide an independent PQ flow, which is contrary to the myth created in the last 2 decades. So what do we take away from this presentation? The takeaway is that I presented the basic power flow control concepts, most commonly used power flow controllers, future trends, and some recommendations. Now, new transmission capacity can be obtained by either building a new transmission line, which is a long and costly process, or harnessing the dormant capacity of the existing transmission lines, which might be a quicker and cheaper option. The smart power flow controller is a functional requirement-based cost-effective solution. Its usage is more relevant today than before, considering the increased demand of electricity due to electric cars, etc., and an effort to reduce the loss in the line, thus reducing the global warming. The design objectives of a UPFC are to be reliable, efficient, cost-effective, free from component obsolescence, and environmentally friendly, portable, and interoperable to meet the needs of the utilities worldwide. Now, my presentation would not be complete if I at least do not briefly mention one other power flow control topology, namely shunt-shunt. In comparison, the autotransformer is a shunt series topology, where the shunt winding is a high voltage winding and low current rated, and the series winding is a low voltage winding with high current rating. Therefore, the overall power rating of these windings is a small number. However, if we need a galvanic isolation between these two windings, then we use a two-winding transformer, which we call shunt-shunt topology. In this configuration, both windings are high voltage and high current rated. Therefore, its rating is much higher than an auto transformer. But if we need it, we use this higher rating topology, even it costs more. 2 decades ago, I had the privilege to work on a project that we call by many names, but it's essentially a electronic transformer. Now, what is an electronic transformer? Well, it must be used as a transformer. The purpose was to connect this transformer to 2 AC networks, and those networks were asynchronous. We're connecting one asynchronous network with another asynchronous network with this electronic transformer, and our objective was to transmit 36 megawatts from one network to another. Now, we could not use a regular transformer because regular transformer has to work with one frequency. And here is a perfect application. Even the cost is higher. We had to use this topology. So we took 2 inverters back to back and connect them at their DC terminals. The AC sides are connected with the 2 networks with 2 transformers. The project was justified even with a higher cost shunt-shunt topology over a low-cost shunt series topology, simply because the shunt series topology cannot be connected with 2 asynchronous networks. So now, our tax dollar is at work to modify this shunt-shunt circuit to replace the DC link with an AC link. Now, why is AC link? Well, because these 2 transformers, which are connected on 2 sides of the inverters, now need to be put into the middle because there is an isolation needed. Now, the middle is DC, so it needs to be made to be AC. So this DC needs to be converted to AC so that we can use the transformer, and then AC needs to be converted to DC, and then we can continue. Now, these transformers also were acting as filters, not just isolation. So because these transformers are gone now we need 2 sets of filters at the both ends. And notice that this transformer has 9 windings compared to 6 windings in the old transformer. Now, this was described in last month's IEEE Spectrum magazine, and the author's claim is that traditional transformer is bulky, oil may leak, the LTC will be worn out. So we should take the old traditional transformer of 19th century and in favor of this proposed new solid-state transformer. Please look at that article, and it has a lot of thought-provoking comments. Now that brings me to the last slide, and where I have a favorite quote from Steve Jobs. He said that one of the things I've always found is that you've got to start with the customer experience and work backwards to the technology. You can't start with the technology and try to figure out where we are going to try to sell it. Now here is the kerosene lamp that I used in my high school years. Here is the kerosene lanterns that billions of people use today. The question I ask, does anyone care for these ever-growing populations who have never used electricity? In my last 3 decades of career, I witnessed many new ideas for supposedly making our grid better. In reality, after spending hundreds of millions of dollars for the sake of doing something new, everyone said, oh, it was a nice project, but we really don't need it. Let's move on. The century-old PERL is still the most widely used power flow controller today. No one seems to be concerned about the unnecessary line loss and additional contribution to the global warming that a PERL creates. So let's keep what's good in a PERL. It's proven and reliable transformer and LTCs that utility is used to using it. Let's redesign it to operate as an impedance regulator. This will create a power flow controller that a utility can afford. It will reduce global warming. Considering the concerted effort worldwide to bring a reliable supply of electricity to this vulnerable 40% of the population, let's use our limited resources wisely, and let's use a smart power flow controller that can improve the process of power delivery everywhere, eliminating the waste and meeting the utilities' need worldwide at an affordable price and make our grid truly smart. Mr. Moderator?
At this time, if you would like to ask a question, please locate the question and answer panel in the bottom right-hand corner of your screen. Type in your question, select all panelists, and click Send to get your question in the queue. The Q&A will be moderated by Phyllis Caputo. Please hold while we poll for questions.
Okay, thank you, Caitlin, for that very informative webinar. I have a bunch of questions that came in. The first question, what does these types of voltage regulator influences on the stability of the network? And that was back around slide 16 that came in. Hello, can you hear? Caitlin, can you hear me?
Slide 16?
Around slide 16, that question came in, yeah.
So slide 16 shows the benefits of impedance regulator over a PAR, phase angle regulator. It does not address any voltage regulation whatsoever.
Was there any slides near there? Because that's when it came in. So the question again was, how does these types of voltage regulator influence on the stability of the network?
I have spoken very little about voltage regulation. My presentation is power flow control, and the slide that I'm showing right now on the screen, slide 14, is an impedance regulator, which is based on impedance regulation for power flow control. So it is not the voltage regulation. If you really want to use voltage regulation, and money is no problem to you, you can have open checkbook, then the best voltage regulation technique is right here, which is implemented with a STATCOM. So if you want to regulate your voltage and have the highest stability, by all means, use this one.
Okay, thank you. My next question is, why has the SEN transformer concept not taken up by a larger power manufacturer in the past?
Past means in last 10, 15 years?
That's just a question. It doesn't say how many years.
Without knowing who is asking that question, I really cannot give you a straightforward answer. But most straightforward answer that I can give you, I cannot read somebody's mind. So you have to ask manufacturers and ask them why they don't use it.
Okay. All right. So let's ask another one. What kind of volume for the smart power flow controller has been forecasted for potential deployment?
Well, smart power flow controller, as I showed you an example, it is a combination of anything that we have today, and it can be used for, it can be used to use all the solutions that we have in the most cost-effective manner. So it is not something new thing. It is maybe something new, maybe something old, but it is the best of everything that we have today, and let's combine them and get the best that a utility needs. In contrast, we see that for a new application, we build something, and then we commission it, but then we don't use it. And we give a fancy name for these installations and the new technology. So what I am saying that a smart power flow controller has to use a smart way, and that takes all the best features of the existing power flow controllers that exist, and if something is broken, just fix that part, but keep the one that is working. So you have to define the functional requirement base, and then you have to find the most cost-effective solution that give you most return on investment. That is the smart power flow controller.
Okay, thank you. What type of switches are used in the UPFC inverters, and how are they triggered?
The one that I just mentioned, inverter-based UPFC, which is the one way to build a UPFC, that inverter is using controllable switch. And I mentioned it. What is controllable switch versus uncontrollable switch? A thyristor is an uncontrollable switch. Once you turn it on, it naturally turns it off. But a controllable switch is you decide when to turn it on and when to turn it off. And this is the one that is needed to build a DC to AC inverter, and that is the building block of a power flow controller, UPFC or STATCOM or SSSC. So the switching frequency, the ones that we used at Westinghouse, they were all 60 hertz frequency. so switching once per cycle. But then if you use another topology, you can go up to manufacturer's recommended switching frequency, and typically 2 kilohertz.
Okay, great. Are there any steady state and dynamic models developed for use with smart power controllers / SEN transformers to use within industrial simulation software?
Yeah, there is an effort right now underway to do just that. So if whoever asked the question can write back to me, I can give more information. But there is the transient models are available, time domain models, and we have published extensively on this matter. I can point to various papers that talks about real-time simulation, but the load flow models that are being developed right now.
Okay. We also have a student who's listening, and he'd like to know if there are some good articles or books that clearly explain the basics of the power flow line, reactance, and the power angle.
Oh, the best book was written by us. My boss, who is the guru in this subject, he wrote a book first, which inspires us to write a book. But before you delve into his book, which is pretty high level, we had to fill in the basics. So read the book that I have had in slide number 5 here, and on the right side. And then read the book written by my boss, and that will give you all there is to know in this technology.
Okay, great. Another question, considering PV grid-tied inverters, as inverters don't have inertia, a considerable load change on the grid side might cause frequency oscillations which are harmful. Are there solutions presently?
Well, that is also one topic of discussion, that all the inverters that we have is very low inertia. As I showed you, the response time is in 2 milliseconds. That was a 100 megahertz step. Yeah, one would think that inverters may not be all that useful in power grid, because power grid is used to have inertia. But with intelligent control of inverter, you can make it look like a machine. I mean, we do that routinely. We have a machine that we used for in a test. But then recently we replaced that machine with an inverter with an intelligent control. That machine looks just like the inverter looks just like a machine. So look at the Power Electronics magazine in the last few months or so. There is a cover page shows you how to a proposal, of course, how to make the Power Electronics inverters look less fast acting than what it is. So it should have more inertia. The intelligent control are also in the process of being developed and proposed. So it is not really per se a one fast-acting device, the inverter. It can be made to operate as a slow-acting as well, so that the inertia seems like it's a virtual inertia would be built into the inverter control. And you can write to me. I'll point to you the right direction, the information that I have.
Okay. What would be the approximate cost of a 500 MVA and a 750 MVA SEN transformer? How long would it take to develop one and then commercialize?
Well, according to our calculation, it should not cost much more than the phase angle regulator. So whatever time a phase angle regulator takes, it will be the same time as SEN transformer takes. Because what we are doing here is taking the components, transformer tap changers that are used in phase angle regulator routinely. We're keeping what works. What we're changing is the control, the way the phase angle regulator works. So there is no difference in that way, except the way we operate those components. So according to what we know from our partner manufacturers, it should take the same amount of time as it takes to build a phase angle regulator, and the delivery time and the cost, everything should be not much more.
Okay, great. All right. Currently, lines are uprated almost 200% in line currents. using ACCC instead of ACSR. Does the high Q problem still exist in such a solution?
Wow. You have to repeat that question again.
Okay. All right, ready?
Yes.
Currently, lines are uprated, maybe that should be graded, I don't know, uprated or upgraded almost 200% in line currents using ACCC instead of ACSR. Does the high Q problem still exist in such a solution?
I have to know that question and answer more deeply. I cannot answer on top of my head.
Okay, well, I'm going to send you a list of questions, so that'll be in there.
That'll be interesting.
Okay, and finally, what kind of maturity of the SIC and or the GAN has been assumed in the proposal of deploying high-power solid-state transformers?
High-power solid-state transformer. I don't work on high-power solid-state transformer. All I see is that I read the article from the Saqer magazine last month to find out that this is one project being developed using my tax dollars. So I had to make a few comments. But I don't know. You have to ask the author. There is a link on that magazine at the bottom and put your comments in like many other people have done and ask what kind of switches they have used to build this one. But I have no information. I'm just commenting and giving my opinion, looking at the claim of the author from what has been done 20 years ago to what they are trying to do, and just from the high-level topological point of view, I'm just making my observations that these are the components we have to use for the reason I stated to connect two asynchronous lines. Now, these are the components being proposed to replace the transformers that we use from 19th century. But what particular components they use, you have to ask the author.
Okay. Final question. Do you see applications for the SPFCs in distribution grids for integrating distributed energy resources? For example, small-scale renewable generation like commercial PV from 50 kilowatt to 2 megawatt, for example.
Yes. Yeah, that is one of our idea to demonstrate in a low voltage, low power level of the first prototype unit. So I suggest whoever asked the question to contact me because I have to ask you a few things, maybe more. I don't have on top of my head. One thing I want to know is when you talk about a solution, you must define what your need is because not all solutions meet your need. So when you define your need, one thing to ask, you need a solution. How fast do you want to operate that solution? What's the response time it should be? And what your need is, we can go backward, as the last slide I had, that work from a need and then go back to your proposed solution. So based on your need, I can tell you whether the mechanical tap changer, which takes typically seconds to change steps, to milliseconds, which would be needed to use a high-power thyristor switches or maybe inverter switches. But it all depends on what your need is, and we can work backward to tell you that what you need.
Okay. Well, thank you very much. Cole, we're going to go back to you.